Shengbo Wang from USC. So it's a very different topic. So it's about Bellman optimality of average reward robust MDP.
Thank you very much for the introduction, and I want to thank all the organizers as well as the Isaac Newton Institute for organizing such a wonderful event. I first need to apologize that so there's something wrong with my ear, so when I speak it hurts, so I might need to stop, like take a few seconds during my talk, so I want to apologize first. So today I'm sharing this recent work on Bellman optimality of average reward robust Markov decision process with a constant gain. So this is a work done with my co-author Nian Ci from Hong Kong University of Science and Technology. So let me provide a brief motivation behind this line of research. So first, let me introduce the notation for average reward MDPs. And throughout this workshop, we have seen a lot of MDP discussions, and I'm using a slightly different set of notation. Here, we're restricting ourselves to finite states and action space models, and I'll also talk a little bit about how to generalize this to infinite state space as well later in the talk. And so we're going to use S and A to denote the state and action spaces. And the state process will be denoted by this xt, and the action process will be denoted by at. And there's a transition kernel in the system that is denoted by this small letter p, which basically describes the conditional distribution of xt plus 1 conditioned on the current state xt and current action at. So I'm also going to consider this very simple inventory example, as Jose and also others considered. So basically, the inventory model works as follows. The inventory level at time t plus 1, so that's xt plus 1, is equal to the inventory level at xt plus the number of inventory that I ordered to be delivered this morning, so that's at, minus the demand you observed during the day, so that's dt. And we take positive part to make sure that the demand goes not go below 0. So this is the standard linear recursion. And in this setting, if we further assume that this demand process is an IID sequence, then this falls into the Markov decision process territory. And in particular, in this setting, the transition kernel would be given by this probability here, where this distribution, so the random variable d under distribution p, so under this measure p has the same distribution as the IID sequence. So in this talk, I'm going to consider the general randomized history-dependent control policy. And since we're in the finite state and action space setting, so the reward function is a mapping from state and action, and it's without loss of generality to assume that it maps the state and action space to some subset of 0 and 1. So our goal is to find, so in the classic MDP setting, our goal is to find a policy that maximizes this expected average reward as n goes to infinity. And here we're taking lim sup, because for a general history-dependent policy, there could be oscillation in the average reward. Hence, you should consider either lim sup or lim inf to make sense of this. And here I'm choosing lim sup. And of course, all the theory carries over if we consider lim inf as well. Yeah. So as we all know, so MDP enjoys very remarkable applications in modern dynamic decision-making environment. And in particular, I think a lot of these empirical successes of MDP models stems from the dynamic programming property, which in this average reward case is saying that the optimal average reward as well as the optimal policy can be characterized using a fixed point equation. So in particular, this is called Bellman equation in the literature. And an important corollary to this is that stationary deterministic Markovian policies are optimal. And this is a good news for both the statisticians as well as optimizers. Now we only need to searching over a much smaller space of policy in order to achieve optimality, so compared to the general fully history-dependent policy class. However, so this assumption, this Markov optimality is really, it really holds under very fragile assumption. in particular, as I said earlier, in this inventory control model, we need to assume that this demand process is somehow IID in order to have this stationary Markovian optimality. And especially in this inventory model, one can, of course, imagine that the demand process could be correlated, as well as there could also be dependence on the historical actions of the inventory manager. And so this plot is the same one that Jose shows yesterday. So this is the same data set where I'm plotting the autocorrelation function. And as you can see here, this demand process, the autocorrelation function shows a demand process that is very far from being IID. And here, if you note that there are not only these high frequency oscillations, but also there are these macroscopic trends. So these high frequency oscillations are actually coming from the day of the week effect. So this Monday correlates with the next Monday. However, these lower frequency oscillation, they do not appear to be correlated with any yearly cycle. So I do not have a good interpretation of what's going on. And that's particularly suggesting the point I made earlier. It's very hard to characterize what's going on within the demand process. So another concern of applying these MDP frameworks stems from the reinforcement learning community, where in a lot of applications, we want to train RL agents within a simulated environment and try to deploy it into a real environment. And such applications include, but not limited to, robotics, like energy systems, finance, and advertisement, RL with human feedback in large language model fine-tuning, etc. And the concern there is that the simulated environment might not faithfully represent the properties or the structures of the true deployment environment. Hence, there could be some misspecification or mismatches between the deployment environment and your training environment. So here is a small clip. Sorry. So there is a small clip of a research done by OpenAI, where they're training two sets of agents playing a game of hide and seek. And as you can see here, so the red agent on the left uses a very peculiar strategy. So by slamming itself with the wedge into the wall, it is able to launch itself over this wall here and observes the blue players immediately. And so although this is it's a very impressive policy, and also it's impressive to see that these RL agents can really find such an interesting policy. But what happens here is actually that I suspect that there's some bug in the system that allows this agent to do this. So if you observe this wedge here, it gets launched to infinity very fast. So I think there's some bug in the simulator. And hence, if we just patch this bug, suddenly this policy wouldn't work and the agent would be set. And so therefore, this shows that there could be some robustness concern when you see this type of policy showing up. Okay, so the previous discussion really shows us that these MDP model, when we are trying to apply it to real settings, could be misspecified. And here I want to emphasize that these type of misspecifications are particularly bad for average reward criteria due to the fact that the average reward are very sensitive to misspecifications. And let me give you a mathematical example, very simple one. So this is the simplest MVP you can think about on two states, and no action, so very simple. The reward will be 1 if you stay in state 1, state X, and the reward will be 0 when you are in the second state. And so suppose that this model is misspecified by a very small amount, delta. So this delta can be arbitrarily small. So originally, if I'm at state X, the average reward will be 1. But no matter how small the delta is, the average reward is actually 0 in the second case. So this basically shows that the average reward criteria is very sensitive or discontinuous, if you wish, in this perturbation of delta, right, of order delta. So regardless how small the delta is, the average reward will jump to 0. And therefore, this motivates our study to try to find a robust decision process formulation. And also we want some form of tractability in terms of like Markov optimality, so extending the successes of the Markov decision process. Okay, so that's the motivation. Let me now move on to a concrete formulation. So we're going to use a adversarial robustness approach. So if you compare, this is the classical optimal average reward versus the robust variant. So we observe that there's an infimum suggesting the presence of an adversary that is placed between the supremum over controller's policy, which can be history dependent, and also the average reward. So the interpretation here is that the adversary can observe the policy chosen by the controller and target the policy chosen by the controller and perturbs the distribution of the process so as to minimize the reward achieved by the policy. And so on the flip side, now the controller needs to optimize knowing the presence of an adversary. So this will force the controller to choose a more robust or conservative strategy. And so this is the robustness formulation. And in our paper, we're going to consider two types of adversary, one being history dependent, the other being stationary Markovian. So first, for the history dependent case, the dynamics works as follows. So that we use this HT denotes the whole history up until the current state XT. A history-dependent adversary basically chooses a sequence of conditional distributions, each of them representing the conditional distribution xt plus 1 conditioned on the entire history HT, as well as the current action AT. So then it's not hard to show that under a pair of controller and adversarial distribution policies, both of which can be history dependent in general, this expectation or the probability measure on the sample path space is uniquely defined. And so that governs the dynamics of the process. So on the other hand, for a stationary Markovian policy, adversary, so this is basically symmetric to the stationary Markovian controller's policy, it basically chooses a sequence of transition kernels. So let's say in the stationary policy, they choose a sequence that is one of the same conditional distributions. Now the adversary chooses transition kernels. So basically, this kernel maps tells us the distribution of xt plus 1 conditioned on xt and at. Yeah. So this is the dynamics. And remember that our goal is to achieve a formulation that allows us to make decision more robust. And in order to achieve that, we do not want the adversary to be overly powerful, because otherwise controller cannot do anything against such a powerful adversary. So we need some way to constrain the power of the adversary. Right, so next I'll be discussing some ways to constrain the power of the adversary. So let's start from the simpler case. So it's the stationary adversary. So now the adversary basically chooses one single transition kernel and fixes over the entire time horizon. And because of this, it's natural to constrain the adversary by saying that I'm only allowing the adversary to choose within a subset, say calligraphic P, which is a subset of transition kernels. Right? So this is quite natural, but it turns out that there's a caveat that if we choose this type of adversary, or if we use this type of adversarial constraints, then typically there's no dynamic programming characterization of the optimal policy or the optimal average reward. And this is a known result, at least from 2013, by this very seminal paper by Wisserman et al. So instead, what we're going to do is we require the adversary to choose its distribution for every fixed x from a ambiguity set, calligraphic P sub x, so which is a subset of mappings from the action to the distribution of the next state. And equivalently, this condition can be think about as I'm letting this calligraphic P, so the subset of kernel, to be some product, Cartesian product of these marginal ambiguity set P sub x. And then we require the adversary to choose from this product ambiguity set. So this is called S-rectangularity, and it's very related to the current action unawareness that Jose was talking about yesterday. Okay, so we can further extend this S-rectangularity to the history-dependent setting by requiring that the adversary, the history-dependent adversary, to choose its conditional distribution within this P sub xt, where this xt is the last element of the history ht. So this is the S-rectangular adversary model. Okay, so now with this adversarial dynamics in mind, let me also introduce a very important concept here called constant gain. So we say that a robust average reward MVP have constant gain if this optimal robust average reward does not depend on the initial state x. So in particular, we're going to use this alpha bar to denote this optimal constant average reward across state. And so this constant gain setting is well motivated in the classical MDP literature because so typically in many operations applications, there are some natural constraints that under a reasonable policy, you're going to induce a stable system. Hence, the stable system will converge to a unique steady state, and that will guarantee the constant gain, so initial state independent gain. Yes?
Time passes on, couldn't you learn the adversary's behavior?
Yes, so that's a very important question that I'm going to talk about later. Yes. Other questions? Okay, so on the other hand, compared to the general gain average reward classical MDPs, there are far more MDP or reinforcement learning algorithms for this constant gain setting. So algorithm foundations are much better established for constant gain MDPs. So, however, because we're studying this problem in the robust setting, our natural question to address is that when do we actually have a constant gain robust MDP in some sense, some form of robust stability. And also, we want a dynamic programming characterization. In particular, we want to show that certain class of Markovian policy is optimal. Can we do that? And I want to remark that actually, for general gain robust MDPs, it turns out that the dynamic programming also, in general, would fail. So that's why it's also important to first consider constant gain robust MDPs. So let me also connect our result with work in the literature. And unlike the average support setting, the discount robust MDP literature have been giving us relatively complete answers to dynamic programming questions. In particular, all of these works in the past 20 years basically provides us almost a complete answer. I won't say almost. There are some remaining interesting questions to be discussed, but the current literature is quite satisfactory for the discounted case. However, the average reward case, the literature is much less, and in particular, as I said earlier, in the general gain setting, this Grant-Clement 2023 paper actually showed that in general the result is negative. You cannot have dynamic programming. And there are some positive results in the constant gain setting, but under much restrictive models, so S-rectangular unichain, and also there is some other contraction type assumption here. So going back to our paper, so we want to show a dynamic programming equations or dynamic programming principle, and it turns out that it's really relatively easy to postulate an equation for which if the dynamic programming holds, then this should gives you the optimal value. So we postulate this dynamic programming equation or constant gain robust Bellman equation. So the solution to this equation is the pair, so V star and alpha star. So this is called the constant gain equation because alpha star does not depend on the state. So with this postulated equation, the issue that we want to address can be reformulated as follows. First, if we assume that a solution to this equation exists, does this solution characterizes the optimal average reward, as well as does it characterizes the optimal policy? And also, do we have Markov optimality? And secondly, when does a solution to this equation exist? Right, so I'm going to answer both questions in the rest of the talk. So yeah, so because this workshop is on bridging learning and stochastic control, I want to say that so this dynamic programming principle has a lot, so it will tell us a lot about learning. So actually, all of the existing, not all, but most of the existing algorithm in the machine literature on reinforcement learning uses these dynamic programming equation as a tool to achieve learning. And in particular, in this robust, in the robust MDP setting, actually there are already results of the form that if we assume that the optimal average reward is characterized by this equation, then we are able to learn with this error guarantee. So, so now it's left to show that this is indeed characterizing the optimal policy. Right. And so this is going back to the question we want to answer, and I'll answer them one by one. So first, first we assume that there exists a solution and see what happens. And we show that the following theorem holds. Assume that there exists a solution pair, V star and alpha star. So if the adversary is history dependent, then we have the dynamic programming. So you can show that this alpha bar is equal to alpha star. And because this alpha bar is uniquely defined as this optimal robust average reward, it's unique. So the alpha star must be unique. And also we have Markov optimality, as well as the optimal policy is characterized by the solution of this robust Bellman equation. And on the other hand, something very interesting happens for the stationary case. So when the adversary is stationary, in general, we do not have this alpha bar equal to alpha star. And under some condition, we can show that this alpha bar equal to alpha prime, where this alpha prime is the solution of another Bellman type equation, where interestingly, the inf and the sup ordering are actually getting interchanged. So, so moreover, the V prime as part of the solution to the second equation does not give you a good policy. And in fact, you need to use online reinforcement law policy to achieve optimality. So this is another bridge between reinforcement learning and stochastic control, because now I'm having a stochastic control, robust stochastic control problem, and there's no learning needed. So there's, you know everything, stochastic kernel as well as the reward function. But here we're showing that you need to use these online reinforcement learning policies to actually achieve the optimal average reward in a stochastic control setting. So it's sort of like a bridge between reinforcement learning and stochastic control. Okay, so let me give some insights to both of these results, why they hold. So the first one is basically dynamic programming principle, and verification style argument will show us that this works. Oh, by the way, I want to mention that so this interchange of this inf and sup is not a strong duality type result, because if it is, then you would have alpha star is equal to alpha prime. But here I'm just claiming that this alpha star does not equal to this alpha prime in general. So for the history dependent case, basically everything is like applying the verification style argument. You plug that value function you have as the solution into the dynamic programming, into the sample pass problem, and by identifying some correct martingale, you're able to argue that that policy gives you the optimal robust reward. So I won't go into too much detail. This is basically the standard argument. what's more interesting is this stationary case. So, the basic idea works like follows. So now suppose that so recall that the adversary chooses a kernel and fixes over the entire time horizon. And now suppose the controller uses a reinforcement learning policy. Then under some irreducibility type assumption, because by the nature of using reinforcement learning policy, you're going to learn the optimal response against this matrix or this kernel P, right? Basically, by using this reinforcement learning policy, the controller is able to achieve this alpha P, which is basically the optimal average reward if the adversary chooses P. So the controller using a reinforcement learning policy is always going to achieve this alpha P. And so what the adversary can do now is to take infimum on both sides of this equation, right? So the controller can always achieve this, so the adversary will just infimize this. And by taking infimum on both sides of the equation, you see that you get an infimum in front of the supremum. So this basically is the idea of the second part of the theorem. So next, let me say something about the existence of a solution. And of course, in general, we do not have the existence of solution. Otherwise, that equation won't say constant gain, average reward, robust Bellman equation. Right? So in this setting, obviously, the gain is not constant. So if you are at state X, the reward is 1. State Y, the reward is 0. So of course, you try to solve it. You find that there's no solution. So in particular, so we think about, so if we look back at the previous theorem, we find out that the previous theorem says that if the equation has a solution, then that solution must correspond to the average reward under a history-dependent adversary. So this is saying that a necessary condition for the existence of solution is actually that the optimal average reward is state-independent under a history-dependent adversary. So therefore, in order to postulate or impose conditions to guarantee the existence of solution, we first need to make sure that that particular condition will imply state-independent optimal average reward when the adversary is history-dependent. So fortunately, this type of condition exists in the classical MDP literature, and so this notion of weakly communication really helps us to have these state-independent optimal average reward behavior. And so let me briefly talk about what does weak communication mean. So we say that a stationary controller policy pi is weakly communicating if the decision set of the adversary is such that the state space can be partitioned into two parts, so the blue parts and the red part. These blue states are transient states in the sense that regardless which kernel is chosen by the adversary, after several steps, they will always end up in the red states. So these states are transient. The red states are communicating. So communicating in the sense that for each pair of starting and ending state within these communicating class, there exists a kernel such that it will leads the starting state to the ending state. So here you see the green one leads the star to the diamond, and this orange one leads the star to this diamond. Yeah. So each pair, you have a kernel that does that. So that's weakly communication. And so with this notion of weakly communicating controller, we are able to show the following theorem. So if all the stationary controller are weakly communicating, and we said we have that, we assume that this P is X-rectangular, so it can be written as the product of the marginal ambiguity sets. And also very importantly, both the controller's policy class as well as the stationary controller policy class as well as the adversary's policy class needs to be compact. And so and under these conditions, we can show that a solution exists. And so this compactness imposes a lot of difficulty when we are trying to generalize this to infinite but countably many states and actions. So in the discounted setting, a lot of the results can generalize, but in the average reward, we find it's very challenging to really generalize this to infinite state action space settings. And okay, so we show that this holds. Although weakly communication is it's a standard assumption in the classical MDP literature, and it's not hard to check. Here I'm also showing some corollary that is more easier to work with and maybe more intuitive. So a solution exists if the set is S-rectangular compact and any of the following holds. So first, if for any pi there exists a p such that this by applying pi to this p, you get an irreducible kernel. So the second one is that for all pi and all p, this p pi is unichain. So irreducibility is a stronger condition compared to the unichain. So irreducible means like every state communicates with each other, and unichain means that you can have a closed communicating class and some other transient state. So under this stronger notion of irreducibility, we have that we only need that there exists a p, but for the unichain setting, we need basically it holds for all p and pi. Actually, so with this corollary, we can extend it to a further corollary, which is much more interesting and applicable. So this is about distribution modes. So as in like previous talks, in Jose's talks, as well as in previous DRO talks, we typically use Wasserstein total variation, or in the discrete context, there's this LP balls to characterize ambiguity sets. And if we use these type of ambiguity sets, then it turns out that a solution will always exist. Notice that here I'm only using these, I'm specifically ignoring the KL or chi-square type ambiguity set. And let's see why this is the case. So basically the intuition is that for these Wasserstein total variations or LP balls, the adversary is able to shift, within the LP ball, you have distributions that have full supports. So the adversary can shift the mass to every part of the state space, and hence there exists a P such that P pi is irreducible. So you can go everywhere in your state space. Right. So that's the intuition behind this corollary. So yeah, since my time is up, let me wrap up what we have discussed today. We want to have a robust average reward Markov decision process under the average reward criteria. We discussed the constant gain setting, and we show that under the history-dependent adversary, if there exists a solution, then that solution gives you a dynamic programming principle. And on the other hand, we also show that under weakly communicating assumptions, such a solution does exist. Oh, it seems that, yeah, sorry. So also, for the case when the adversary chooses stationary policies, our online reinforcement policies are actually optimal for the controller. So here I'm listing some questions that some of them we have some answer to, but largely we don't. But I think so these are very interesting questions. For example, what about non-constant gain setting and infinite state and action space models? And we said that we do not have dynamic programming for a non-rectangular or this general constraint adversary. But it turns out that that's not exactly true. We have some characterization of the optimal policy there. So it's not in terms of a dynamic programming equation, but we have some form of characterization. This is an ongoing work. And so in general, one might not after full solutions to these robust Bellman equations, what about if we have epsilon solutions? So epsilon solutions typically will also lead to dynamic programming principles, but we do not know when does these epsilon optimal solutions exist. And so finally, is there any like necessary sufficient condition characterization for the dynamic programming principle? So basically, it's a generalization of the previous question. Okay. So that's the end of my talk, and thank you. I'm happy to take any questions.
Thank you. Are there any questions?
A comment for your questions. You might want to look at some of the ergodic backward SDE theory that was developed about 10 years ago, because I know Andy Allen and I addressed very similar questions there and might have answered some of your points, but in a very different looking way of dealing with the problem and under slightly different assumptions.
Yeah, okay, thanks. So actually, I have some, indeed, I have something like to say here. So regarding your question, I think the ergodicity really helps. And when you increase your assumptions on how regular the Markov chain behaves, then you can get existence in uniqueness of solution, as well as you can get like dynamic programming. So that part is for sure. But here we're really trying to see what's the boundary of the assumptions that we can make to guarantee everything works. Yeah. But yes, that's
Well, we have it in continuous time, discrete time, finite, infinite state. We have cases of all types.
Mm-hmm. Yeah, thank you.
So one question, sorry, I mean, is it, maybe I misunderstood the condition, but you, as long as the adversary, you have one adversary, like if the ball mm-hmm. is such that the adversary can produce some, let's see, for any pi that exists policy in the ball. So you could have had a dynamic programming problem at the beginning, right? It's from that assumption, the first bullet, it sounds like you could have started with a dynamic programming problem, like an MVP, mm-hmm. for which there was no constant gain, right? You didn't have like right. And so the minute you put delta positive,
yes,
now everything gets fixed.
Right. Exactly.
Right. So this is not continuous in delta, for example.
Yes. So this is exactly the intuition that I had earlier. So you remember this example?
Right.
As long as you put a delta between all the states, the adversary just can take you from every state to that very it's able. It's not exactly like that, but the adversary is going to connect the entire recurrent class.
Right.
So that makes the
correct. So this is truly like a regularization. Like you could think of you could start with a very ill-posed MVP, right? Maybe it doesn't even have a Bellman equation, is delta equal to 0, and then you include this, and then now you all of a sudden do have a constant gain.
Yes, right. Yeah, that's
so as a just pushing forward this observation, it should be the case that you could get solutions, solutions to the equation that actually have better regularity, for example, as a function of x, more smoothness, more properties that is that something that you see happen?
I think like in the discrete state space setting, this is hard to characterize, right? So
no, I thought you were talking about continuous now, like Wasserstein ball and all of that.
Oh, that is for like discrete infinite state space. It's still discrete. So So I haven't really thought.
There's nothing that prevents you from. It sounds. I think it looks pretty clear that if you just have.
But all of these results need compactness. So when you
that's even with compactness, you can get I can give you a problem that doesn't have a dynamic programming. You don't have DP because you don't have unit chain. You don't have these things. It's very easy. But now and it's compact and nice and right. The minute you actually do this thing. Now, I suppose that the social flow.
It's like let's say discrete infinite state space, but now you're doing Wasserstein things. But that's not compact, right?
No. So you are saying that if I give you like something that is, for example, kernels, right? You just in a compact space. Something that is like a control formulation, xn plus
Right.
1 equal to fxn, everything compact.
Yeah.
Right.
But that's
Your
fine.
theory doesn't hold, no?
Yeah, that's
true,
right.
right?
Yeah.
So then take that case, right? And then what you're saying is like you could start from a situation where you might not even have a solution, or maybe the solution is very badly behaved, and then you add this, and this probably will make it.
Yes. Yeah, I think that's possible. Yes. Right. Although you would go to like what regularity you would need for that to hold. Yes.
Okay, so thank you, and let's thank all the speakers.